Okay, thank you very much. And it's a pleasure to talk at this meeting. So this is a joint work with Miriam Farber, who is a graduate student at MIT. And let me start with motivation for this work. So first motivation is matrix completion problem. So that's the problem of filling in entries of a partial matrix so that the resulting matrix satisfies certain property. For example, it's a positive definite or totally positive or something else. And Miriam, together with two groups of collaborators, looked at a variant of this problem, at the following variant of this problem. So, let me remind you that matrix is called totally positive if all minors of this matrix of all sizes are positive. And it's totally non-negative if they are non-negative. So then the fact is that given a totally non-negative matrix, you can slightly change some of the entries to make it totally positive. So by slightly modifying some subset of entries, we can make all minors strictly positive. And the question is, how can we do it in a minimal way? So how can we modify the minimal number of entries, as minimal as possible? And in particular, if we start with the most degenerate matrix with non-zero entries. So in other words, start with a matrix filled with all ones. So how can we modify as few entries as possible to make all minors strictly positive? So you want to minimize the number of entries that you change. In other words, you want to maximize the number of entries that you don't change. So that means that this question is a question about the maximum number of ones in a totally positive matrix of given size. Equivalently, we can ask what is the number of equal entries? Because if you have a matrix with some equal entries, of course you can rescale this matrix and make all these entries to be one. And once you ask a question about entries, it's not very natural to ask a question about minors, because from the point of view of total positivity, entries are just one by one minors. So we can ask questions about minors of any sizes. So what is the maximal number of equal minors in a totally positive matrix? And Miriam, with her collaborators, prove a bunch of results about these kind of questions, and here are just two of these results, is that if you have a square matrix, then the number of equal entries, square totally positive matrix, then the number of equal entries is of order n to the 3/4. And another result, if you ask about 2 by 2 minors in a 2 by n matrix, that's actually kind of interesting that you get exactly the same order. And this result is based on semi-Redi-Trotter number on point line incidences on a plane. So that's a problem, well, that's a result from asymptotic or extremal combinatorics. Now we can ask, in this work, we want to ask something better. So we want to ask not about the number of equal minors, but about the structure of possible equalities between minors. And another motivation for this work comes from combinatorics of the totally positive Grassmannian. So as some of the speakers today mentioned, so if you look at the totally positive or totally non-negative minors, totally non-negative matrix, so all minors are greater than or equal to 0, and ask which minors are strictly positive. So these kind of questions leads to a very rich combinatorics of positroids, Lie diagrams, Leibniz graphs, and so on. It's related to the cellular decomposition of the positive Grassmannian, positroid varieties, and so on. So there are a lot of interesting results about this question, related to this question. Now we want to understand a kind of more subtle structure of equalities and inequalities between the minors. So in a sense, so this question about positroid is the question about which collection of minors can be equal to 0. Now we want to ask which collections of minors can be equal to each other. So that kind of, I think about this as a kind of higher order question. If you like, this is a kind of question about zeros of a function. That's a question about critical points of a function, in a sense. So maybe we can get some kind of higher positroids or kind of more interesting combinatorics. Okay, so So let me remind you of two definitions. A Grassmannian is the manifold of k-dimensional subspaces in the real space and working over real numbers. And in a concrete way, we can think about this as a space of k by n matrices of maximal rank modular row operations. And the Plucker coordinates are the maximal minors. Now we're interested in the maximal minors of k by n matrix, and they are labeled by this set, n choose k, that's our notation, the usual notation, set of k element subsets in n. So the positive Grassmannian is the subset of the real Grassmannian where all Plucker coordinates can be made simultaneously positive. And similarly, non-negative Grassmannian if we can make all Plucker coordinates non-negative. So, for example, for k equals to 1, the Grassmannian is just the projective space, and the positive Grassmannian is an n-1 dimensional simplex inside of this projective space. So, in a general case, we have a similar story. So, we have Grassmannian. We have Grassmannian, and inside of it, we have some kind of structure that looks like a polytope. It's not exactly a convex polytope, but it still has looks a lot like a polytope. It has a faces of various dimensions and so on. Okay, now we can actually embed k by n minus k matrices to the Grassmannian grkn in a very simple way. I don't want to write it down, but this can be made very explicitly, so that all minors of all sizes of matrix A are equal to the maximum minors of it. So this identifies the space of totally positive matrix with the totally positive Grassmannian. But if you talk about totally non-negative matrices, that's going to be a proper subset of Grassmannian, open subset in the Grassmannian. So, and that means that we can convert all questions about matrices to the language of the Grassmannian. But let me tell you a couple of reasons why I prefer to work in the Grassmannian. Well, one kind of trivial reason is that instead of minors with two sets of labels for rows and columns, so we only need to care about maximum minors with only one label for columns. So somehow all notations become much simpler. We just reduce the number of indices by 2, by a factor of 2. So that's kind of not very deep reason, but it's kind of helpful for conventions. But another reason is that on the Grassmannian we have a cyclic symmetry. On the positive Grassmannian there is action of the cyclic group. And we will see that all kinds of combinatorial objects that are obtained in this theory has this kind of cyclic symmetry. So on the level of matrices, you cannot easily see the cyclic symmetry, but for Grassmannian, it's very natural. So this is why kind of it's better to work on the Grassmannian. Okay, now let me define. Arrangement of minor is an ordered set partition of the set n choose k, for which we can find element of the non-negative Grassmannian such that for the zeroth part, all minors are equal to 0. All minors that sit in the same part are equal to each other, and if you have a minor in part I sub I and another minor in part I sub j, if I less than j, then this minor, with this Plucker coordinate, is strictly less than the other one. Question is, how can we describe this combinatorial structure? All possible arrangements of minors, study their combinatorics, and so on. And as I just mentioned, just a question about the zeroth element, I0, set of minors which are equal to 0, it already leads to a very rich combinatorics. So in this talk, I'm going to assume that I0 equals to empty set. So that means that we are working in strictly positive Grassmannian, and I want to concentrate on possible sets I1 and IL. I'm just going to describe the extremal cases. The first one, we'll call it arrangements of smallest minors. So we have a bunch of minors which are equal to each other and smaller than all other minors. And also we have a question about the largest minors. Okay. Question, case k equals to 0, that's pretty simple, because in this case the Grassmannian is just projective, well, it's just a collection of numbers. We're just asking what are the possible equalities between these numbers. That's basically combinatorics of the braid arrangement. That's a pretty trivial case. But the case k equals to 2 is already very interesting. So in this case, so we have two element subsets, ij, so we can identify them with edges of the graph, and the collection of minors will be a subgraph. Now we are going to arrange all vertices of the complete graph on a circle and we say that two edges are non-crossing if they are literally don't cross, if we present them by straight line chords instead of, and otherwise they're crossing. And we say that the subgraph is non-crossing if any pair of its edges is non-crossing. So, and another kind of subgraphs, if any pair of edges is crossing or shares the vertex, we call them fractals. So arrangement theorem, arrangements of smallest minors correspond to non-crossing subgraphs, and another result, arrangements of largest minors correspond to fractals, to subgraphs where every pair of edges crosses. So let me just show an example, that's much easier to understand. So that's a maximal non-crossing subgraph, which is basically a triangulation of n-gon. And that's a fractal. So every pair of edges either have a common vertex or cross. And these kind of edges of triangulations correspond to a possible arrangement, possible equality between minors, so that all other minors are strictly greater than this. And this fractal corresponds to a possible equality between minors such that these are largest minors. So all other minors are strictly less than this. And that's exactly a one-to-one correspondence. So here are more examples of triangulations. Of course, you've seen these kind of pictures. And of course, you know that the number of triangulations which correspond to smallest arrangements of smallest minors is exactly the Catalan number of all triangulations of the n-gon. Okay, on the other hand, these are examples of fractals. So there every pair of edges cross. So these fractals, well, these are maximal fractals. So they're obtained from, in this case, from a triangle or from a 5-star. In general, we can take any even star and maybe add some number of leaves at each vertex. So this is the general structure of fractals. And the number of such things is actually the Eulerian number A n minus 1, 1. The number of permutations, this is exactly 1 this side. Well, it's 2 to the n minus 1 minus n. Okay. So how can we prove these results? So in one direction, it's pretty easy to see this just from the well-known Plucker relation, free-term Plucker relation. So we have this Plucker relation that basically says that the kind of pair of minors corresponding to a pair of crossing edges equals to 2 ways to uncross this pair of crossing edges. So for example, if you know, if for example delta 1 free equals to delta 2 4, so we have 2 crossing edges, then at least one of the terms on the right should be strictly less than these two guys. That means that this pair of crossing edges cannot belong to the arrangement of smallest minors. We always have a smaller minor. Similarly, we can argue in the opposite direction. So if we have 2 pair of non-crossing edges, say for example delta 1, 2, delta 3, 4, if they're equal to each other, so then the left-hand side is strictly greater than this product. That means that one of these terms in the left-hand side is strictly greater than these two guys. So that means that this pair cannot belong to an arrangement of largest minors. Okay, and in order to prove, so that easily proves one direction, and in order to prove the opposite direction, we just need to construct, for each triangulation, or for each fractal, we need to construct explicitly matrices with given equalities and inequalities. And we can do that. Okay, now that was a warm-up case, now let me do the general case. So in general case, we need to generalize triangulation and fractals to arbitrary case, find some generalization of this. So we need to generalize this non-crossing or crossing condition. And the generalization is called weak separation. Well, generalization of non-crossing graphs of triangulation is called what is called weakly separated sets. So we say that 2 pair of k-element subsets is weakly separated. So if you take their set theoretic differences and arrange them on a circle, they're going to be literally separated by some port in the circle. And a subset of n choose k is weakly separated if any pair of its elements is weakly separated. And for k equals to 2, these are exactly non-crossing graphs. Okay, historical remark that these things were introduced by Leclerc-Zelevinsky in the study of quantum minors. And this is really very much related to the theory of cluster algebras. And Leclerc-Zelevinsky conjectured that had a purity conjecture, that all maximal weakly separated subsets had a same cardinality and they can be connected by a sequence of mutation. And relatively recently there were several proofs of this conjecture. One proof was done by Danilov, Karzanov, and Koshevoy, and another way was done in my work with Suho, Oh, and David Spire. So, and actually now work we constructed a bijection between weakly separated sets and reduced Levy graphs that appear in the study of the positive Grassmannian. So let me just show a picture. I'm not going to explain what it means, but this kind of picture shows a reduced Levy graph, and you see on every face of this graph you have some label given by k-element subsets. So this is an example of a maximal weakly separated set. Okay, so I'm not going to explain it, but these things have an interesting kind of planar structure. Okay, now let me tell you the other side of the story. So how do we generalize Thrakels to any K? So that's a very similar thing. So now you take two subsets, k-element subsets, you take the set theoretical difference, and now we require that they are as much interlaced as possible. So they are literally interlaced, then you draw them on a sort. Okay, this pair of subsets is called sorted, and if you have a subset such that every pair of its elements is sorted, then we call this subset in n choose k sorted subset. And for k equals to 2, that's exactly Thrakels. And these kind of things appeared in the study of by Bernstruffels of Grobner basis in my work with Thomas Lamb on Alkov polygons. So in particular, any maximal sorted set contains exactly n elements, and it also follows from this work that the number of maximal sorted sets is equal to the Eulerian number of permutations of given size, the given number of the sets. Okay, now let me mention the results. First result, arrangements of maximum minors are exactly sorted subsets. Second result, any weakly separated set is an arrangement of smallest minors. And conjecture, we conjecture that actually, again, arrangements of smallest minors are exactly weakly separated sets. So it means that this theorem just claims this conjecture in one direction. Well, it's just one direction of this conjecture. And the other direction we cannot prove it for general K, but we can prove it for K equals to 1, 2, 3, or n minus 3, n minus 2, n minus 1. So how do we prove it? So we saw before that we used kind of inequalities, this Pluk correlation that implies inequalities between products of minors. So in the general case, there is a generalization of these kind of inequalities found by Marx Canberra. So there are some inequalities, I'm not going to write them down, but we can actually use these kind of inequalities to prove the first theorem in one direction, to show that sorted condition is necessary. And we can also prove the second theorem in the same direction, but not for any k, but only for k equals to 1, 2, and 3. Or n minus 1, n minus 2, n minus 2. Okay, so, but somehow for k greater than for Skanderas inequalities are not enough. We have a concrete counterexample, so that shows a matrix. Well, so basically here is a counterexample. So we have a pair of subsets which are not weakly separated. However, we can find element in the Grassmannian such that this pair, the corresponding pair of product of Pluto coordinates is the smallest among all complementary products of all complementary Pluto coordinates. So somehow we cannot use this Canberra inequality in the general case, and this matrix is obtained from these it's obtained, you remember I mentioned the embedding of the matrices into the Grassmannian, so that's, if you embed this matrix into the Grassmannian, then you get a counterexample. So, and here is a challenge problem for k equals to 4. So if we can solve this problem, then we will prove the conjecture for k equals to 4. So prove or construct a counterexample. Just a claim about 4x4 matrices. So if we have two complementary minors of a totally positive matrix, delta 4, 3, so it's marked by this red element, it's just a matrix element, and this kind of minor that's marked by blue stars in this matrix, if they're equal to each other, then we can find another minor which is strictly less than this pair. Somehow, I don't know why, it looks like some kind of not very hard question, but we couldn't prove it. Well, if we can prove it, then that would imply conjecture for k equals to 4, and a similar kind of statement would imply the conjecture for general k. Okay, now, yes?
Any constraint on that other minor?
Any
Any other minor? Anything?
No. Any other minors are positive, strictly positive.
Oh, yeah.
It should be totally positive matrix. But if we have this equality, so that's kind of basically this case up to symmetry. That's the only case which does not follow from Skanderos inequalities. So possibly we need to find some kind of more general inequalities than Skandera inequalities in order to prove this kind of statement. Now, how about the other proof, other direction of the theorem? So for the other direction, we need to explicitly construct matrices with given equalities and inequalities between the minors. And we have such construction. So for the smallest minor, it's really very much related to the theory of cluster algebras. It follows from earlier works that if you have any maximal weakly separated sets of minors, so they correspond to a subset of algebraically independent Fluker coordinates such that any other Fluker coordinate is expressed in terms of these guys by subtraction for irrational expression. That means that if we make all these minors equal to each other, say set all of them to 1, that defines a unique element in the Grassmannian because all other minors are uniquely expressed in these guys. So why? But we need to show that they are strictly larger than these. So how do we see that? That actually forms a cluster, an initial seed of a cluster algebra. And this cluster algebra was studied by Scott. For cluster algebras, in general, we have a Laurent phenomenon. So actually, these rational expressions that I mentioned here, they are not just rational expressions, but they're actually Laurent polynomials in the initial seed. And Fomin-Zelinsky conjectured, and Lee Schiffler recently proved that these Laurent polynomials are not just Laurent polynomials, but they have positive integer coefficients. So that implies that actually all other minors are expressed in terms of these deltas by some Laurent polynomials with non-negative integer coefficients with at least 2 terms. So it means that it has to be strictly larger than this. So if all these deltas are equal to 1 for the initial seed, all other deltas are at least 2 or more. Okay, now let's consider sorted sets. So for sorted sets, the story is a little bit different. So let me define the positive torus. So it's kind of just as a collection of positive real numbers. That's maybe a little bit misleading because it's just a kind of positive octet. Generically, it doesn't look like a torus, but it's kind of positive part of the complex torus. So it acts on the Grassmannian by rescaling forms of the matrices. And we actually proved that for any maximal sorted set, and for any element of the positive Grassmannian, there is a unique way to rescale the columns of the matrix, a unique way, an element in the torus orbit of this A, such that that realizes any maximal sorted set. So we can, so for any maximal sorted set, we can find a matrix. Just start from any matrix, rescale columns in some way, and we can get it. So, here is a remark that for maximal smallest minors, there is a unique point in the Grassmannian that realizes. For minimal, for smallest minors. For arrangements of largest minors, we have more flexibility. Actually, each torus orbit contains the Eulerian number of special points that realize all arrangements of largest minors. So, and this proof is based on the theory of Alpov polytopes. And let me maybe mention a few examples, just give you a few examples of these special points, how they look. And I'm going to give these examples for k equals to 3. And so really we're talking about three-dimensional Grassmannian. So GR3n is given by a collection of n vectors in the three-dimensional space. It's 3 by n matrix. And I'm thinking about them projectively. Instead of vectors in three-dimensional space, I'm going to talk about points on a plane. So the collection of points on a plane represent a point in the positive Grassmannian if these points form vertices of a regular n-gon. Convex, not regular in general, of a convex n-gon. So positive Grassmannian corresponds to convexity in this case. So what I want to do, so I want to rescale these vectors and to make as many equalities as possible. So So, and here are the examples. Here, this is how we can do it for n equals to 5. So, so let's pick a regular pentagon, and I marked vertices of the regular pentagon by the rescaling constants. So by the constants by which we need to multiply these numbers to make as many minors equal to each other as possible. And there are actually up to rotations, there are 3 cases. These where all scaling constants are 1. These where they are equal to 1, 1, and theta, which is, well, actually, one person told me that in a serious mathematical paper, I shouldn't mention golden ratio. Because that kind of makes a bad impression. That's, you know, but, well, actually, but it happens that these constants in this case involve golden ratio. So, and in general, we get, in one case, we have 1 rescaling, here we have 5 possibilities because we can rotate it. Here we have another 5, we get 11 rescalings. That's the Eulerian number. And this is how these rescalings look like for the hexagon. There are 10 types. Okay, so you can look. There are a lot of possibilities, and if you add up all possibilities, you get 66, which is also the Eulerian number of permutations of size 5 with 2 descents, and so on. Okay, and so maybe just let me mention a few other things. So as a special case, we can specialize these results to matrix entries. So because remember this embedding of matrices into the Grassmannian, in particular matrices of a K by n minus k matrix correspond to some special minors, special Blucher coordinates in the Grassmannian. So we can specialize those notions of weak separation and sorted notions to these minors corresponding to special matrix entries. And in this case, maybe instead of reading this, I'll just show you this slide. So the theorem is that equal are maximum ranges of equal largest entries in a totally positive matrix. So we have a totally positive matrix, and now we want to say which collection of entries can be made equal to each other and greater than all other entries. They actually correspond to a lattice path, so here marked in red, from the top left to the bottom right corner. Of course, there are the binomial coefficients of such lattice paths. And for arrangements of smallest entries, we also have lattice paths. They correspond to lattice paths, but now from the bottom left to the top right corner. So they are marked in blue. Okay, so there is a really kind of duality between these 2 cases. Okay, and so all this that I told so far was about the positive Grassmannian. Now, what about the non-negative Grassmannian? What if we allow some Blucher coordinates to be 0? So many of these arguments will not work. So in this case is really different. So and the simple reason that this Blucher relation, now some of the terms can be equal to each other, so we do not get a strict inequality. We only get a weak inequality here. So it means that most of the arguments that I mentioned will not work in this case. But there are some results. At least for k equals to 2, we could the maximal number of equal 2 by 2 minors. Actually, in this case, we can actually achieve much more equalities between minors. So if we allow minors to be equal to 0, that allows a lot of flexibility. And there are some numbers, explicit numbers that we can calculate. And I think okay, let me show just one more slide. We discussed smallest minors arrangement and largest minors. So question, what do we have between these 2 extremal cases? So is there some kind of row structure that interpolates between weakly separated and sorted sets? So is there a common generalization of plus algebras and Alpov polyols? Can we kind of put these 2 extremal cases into one single picture? Well, next question that I just mentioned is how to extend it to the non-negative Grassmannian. Another thing is that these results seem to be very much related to true positivity. Because we use Kandera inequalities, and in an earlier work, we applied Kandera inequality and Rod's Kandera results to prove some true positivity results for differences of products of true functions like this. And actually, the arguments in the current work are very much related, looks very much similar to these kind of true positivity results. So is there some, can we say something more explicit how all these studies related to stereotypical minors? Can we get more general Schur positivity results? And question is, how to generalize Cantor inequalities for minors? Can we get something more general that would imply our conjecture? Okay, and that's the last slide.
Do we have any last questions to speak with?
Have you considered a similar question for flags?
Not yet, but that's natural question is how to, another open question is how to generalize it to flags, partial flag varieties and so on.
Is there an easy correspondence between those sorted sets? I haven't seen that before, and ordinary numbers. I mean, why?
Yeah, there is explicit. So in our paper with Thomas Lamb.
There's an alcove polytope?
Yeah, on alcove polytope, that appears in the paper on alcove polytope, and there is explicit correspondence between sorted sets and permutations to a given number of these sets.
Anyone else?
So do you have a conjecture for these generalized Sandera inequalities? Like what?
Oh, not yet. so,
Okay.
But that would be, maybe that's related to this your work on immanence. So I hope that maybe we can use somehow to prove this conjecture, but we don't know how to do that.
And do the inequalities you're looking for, do they expand non-negatively in terms of cautionalistic immanence, or?
Maybe. So we hope that this can be done, or something like this can be done. But yeah. So we hope, I really hope that this kind of cautionalistic immanence can be used to prove or maybe disprove this conjecture that I mentioned.
So let's thank the speaker again. And I have the pleasure of closing the conference. I really want to thank our hosts, DePaul University, and especially to Bridget. She has been an absolute